that a finite product of countable sets is countable. Today we're going to construct our first uncountable sets by showing that a countably infinite product of countable sets is uncountable. Remember, we showed two things at the end of the last video. They seemed to be very similar, and yet they reached different results. You can take a countably infinite union of countable sets, and the result will still be countable. So it seems very natural to imagine that if you take a countably infinite product of countable sets, that result would be countable also. But if you remember, last time, instead of looking at a countably infinite product of countable sets, we only proved that a finite product of countable sets is countable. Now, today, we're going to see what happens when you create a countably infinite product of countable sets. You do not get a countable set at all. Instead, you get what will be our first uncountable set. Then, we'll end the video by constructing one more uncountable set, the power set of positive integers. That proof will take some time for us to wrap our heads around, so we'll take our time to make sure we get it. So first, what happens when you take a countably infinite product of a countable set, even a very small one? Okay, theorem. Let X denote the two-element set 0 and 1. Then the set x to the omega is uncountable. Remember, x to the omega is how we denote a set that is crossed with itself countably many times. So we're going to show that given any function from the positive integers to x to omega, this function is not surjective. And from the theorem from last time, that means that it cannot be countable either, because if there is a surjective function from the positive integers into the set, then it is countable. So we're going to prove that none exist. So let's denote g of n like this. So each value of g of n is xn1, xn2, xn3, and so on up to infinity. So each one of these is either 0 or 1, because each one is an element of 0, 1. Remember that each value of g is an element of this set, and this set is an omega tuple of elements from x, right? So all we're saying here is that each value of g is going to be an omega tuple of zeros and ones. Okay, so here we're just specifying which one it is, right? So 1 will go to 1, 2 will go to a different one, and so on, okay? So we can look at each element in that way. Okay, so let's define an element y as an element of x omega. So it's an omega tuple of ones and zeros, right? And we're going to define it by each element here will equal 0 if xnn equals 1, and 1 if xnn equals 0. So what are we doing here? If you imagine for any function of g, we don't care which one, but whatever it is, we're going to have g to the 1 equals some number here. I'm just making this up. And then g2 will be something else, and so on. G to the n will be 1, 1. All right, so these will be anything, but the point is that no matter what the function g is, each positive integer will have a value that is an infinite omega tuple of ones and zeros, okay? So what we're doing here is we're defining y so that its nth coordinate differs from the nth coordinate of the nth value. Okay, so for n equals 1, then if this is 1, then the y1 equals 0. If n is 2, then we go to the second row, and y to the 2 is 1 because this one's 0, and so on. So then g to the n out here somewhere, and then it's the opposite. So the point is that each element inside this omega tuple differs by at least one element from one of the numbers that g sends into x omega. So what does that mean? That means that y is an element of x omega, but y does not lie in the image of g because it differs by at least one number from every element in the image of g. Thus, G cannot be surjective. And that proves that no matter what G is, we can always find an element that does not belong to the image of G in this way. And that's what we needed to show. That means that x to omega cannot be countable, because if it's countable, then there is going to be a surjective function mapping the positive integers into the set. And we just showed that in this case, there is not one. So therefore, x to omega is infinite, and in addition, in some way, it has more elements than the positive integers, which are already infinite. We don't know more what that means, but we've proven that there's at least one set that's at least bigger in some way than the positive integers. So this procedure might look familiar to you. We've looked at this before. This is the common way of proving that real numbers are uncountable. We'll come back to this in a minute. Okay, so we just showed that the Cartesian product of the two-element set 0, 1 to the omega is one example of an uncountable set. Another uncountable set is the power set of the positive integers. So we're going to prove a theorem now that will prove that this set is uncountable. Okay, in order to prove that the power set of positive integers is uncountable, we need to prove another theorem about power sets generally. The result for z plus will follow naturally. This is the theorem that is really hard to wrap our heads around. The actual steps of the proof are simple, but getting to the point where we understand what we're talking about takes some real effort. Okay, so theorem. Let A be a set. There is no injective map F from the power set of A to A, and there is no surjective map G from A to the power set of A. Okay, so the first step of this proof is almost like a lemma. If B is non-empty, then the existence of an injective map from B to C implies the existence of a surjective map from C to B. So the way we do that is we define G of C to be the inverse of F for each C in the image set of F, and then just define G arbitrarily for everything else. So what this means is, if a function is injective, it means that it's monotonic. It means that it does not buckle on itself. Because if it buckles, then the inverse of the function will not be well defined, because there are some elements of the domain that have multiple values, so it's not well defined. But if the function is monotonic, then the inverse will be defined. And then what we know about that inverse function is that it's going to be surjective, because by definition, every element in the domain of a function is mapped to some value. So if we take the inverse of that function, then every element of the range is now mapped to by something in the domain. So that's the definition of surjective. We might not be using the entire domain in order to cover everything in the range. That's not important. It doesn't matter what else is going on in the function. What matters is that every value in the range is mapped to by at least one element in the domain. We know that because this is the inverse of the injective function. So therefore, the point of that is that in order to prove our theorem, it suffices to prove this part, that if there's no surjective map from A to the power set of A, then there can't be an injective function either, because if there was an injective function, there would be a surjective function. If there's not a surjective, there can't be an injective counterpositive, right? Okay, so if we show that there is not a surjective function like this, there can't be an injective function like this. So all we need to do is prove this part, and then this part comes from here. Okay, so let's just first notice that this has to be true, that there's no surjective map, because there have to be more elements here than there are here. Because, first of all, there's an element in this power set for each element of A, right? Like if A is just the set ABC, then the power set has at least one element that's the set with A in it, one with B, one with C, and then also, no matter what is in A, there's going to be some more subsets, as well as the set of all of A, as well as the empty set, and yet there's only 3 elements here in A, so it can't possibly be surjective, right? So this statement makes sense. But notice what we're going to get to here. What this is going to imply is that means the positive integers are countably infinite, right? And there must be more elements in the power set of the positive integers than there are in the positive integers, meaning that there's not a one-to-one correspondence from the positive integers into the power set of the positive integers. So the power set of the positive integers must also be uncountable. Okay, but this obviously isn't a proof, but how are we going to prove this rigorously? Okay, so we take a set A and an arbitrary map. So no matter what G is, G maps A to some subset of A, right? So here's a true statement. No matter which subset it is, that subset either contains A or it does not contain A, right? So if we look at, let's just, when we're looking at this, let's just consider, just as an example, that A is A, B, and C. So the power set then contains the following elements. So no matter which element of the power set G sends A to, it's either going to contain A or it's not going to contain A, right? Some of them contain A, some of them don't contain A. So let's let B be the set of all of the points in A such that G of A goes to a set that does not contain A, okay? So this is why this proof is hard. It's hard to get your head around that. Whatever G is, for every element inside the set, some of those elements are going to map to a set that contains A, and some of them are going to map to a set that does not contain that element. So let's let B be the set of all the elements of A that G maps to a subset that does not contain that element. All right? Okay, so first, how do we write this in set notation? Here's how Monkrez did it. Let B equal X such that X is an element of A minus G of X. It took me a really long time to get comfortable with this set definition. I understand what it's doing, but I'm not comfortable with it. I tried for a long time to figure out a way to clarify the notation, but I finally decided that that's not the issue. The notation is okay, the problem is something else. So the problem that I had is it looks like we're using X before we've defined X, right? We're sending X through this function, but we're still in the process of deciding whether we're even using it or not. That's the thing that I balk at. We've talked about that before. What I finally figured out is my objection is coming from my background in software engineering. I think of functions in the programming sense. They're methods or functions. You have inputs and you have outputs. You take the input parameters, you manipulate them, and then you send them back out. Functions in programming are active, but that is not at all what a function is in mathematics. A function is a map and nothing more. A function in math is completely static. The function doesn't do anything. It is not taking a value as input and returning something else as output. It's not returning anything. The function is just a list of associations. It's like a two-column table. The left side is the domain and the right side is the image. So G of A doesn't mean take A, do something to it, and then return something else. G of A is simply a label that we have put on a certain element in the range of this function. That label has already been assigned. It just refers to a particular element. So the right way to think about a function in mathematics is as an ordered pair, with the domain on the left and the range on the right. So for our set, ABC, we have 3 ordered pairs. There are the same number of ordered pairs in this list as there are in the domain. In our example, 3. So all we're doing with this set is we're looking at this list of ordered pairs and we're looking for the ones where the element on the left does not show up on the right. We could replace each GA with the actual subset that it goes to. So just as an example, maybe G maps A to the power set in this way. So if we look at these three ordered pairs, we see that the set here does not contain A, and the set here does not contain C, but the set here does contain B. So if this was our function, g, then B would contain A and C, but not B. Okay? So could we write this in a way that makes this point, the static nature of G, more explicit? Maybe. But at this point, I'm convinced that the problem I had here was with me not thinking of mathematical functions in the right way as static maps, rather than functions that do something. It's so hammered into your head in software engineering that functions or methods are active, I was completely blind to this point. So to say it again, mathematical functions are not programming functions, despite the similarity of the notation. I'm curious whether anyone else has had this confusion. Thinking back, I think that I've had this prejudice toward mathematical functions for a long time. Hopefully this will clarify some things that may have been problematic before. Let me know in the comments if you've had this same problem, if I've pointed something out to you that hadn't occurred to you, or if it's always been obvious to you that mathematical functions are just maps. I mean, after all, the first chapter of every book tells you that functions are maps. I just refuse to listen. Okay, anyway, on with the proof. Even understanding the definition of B, it's still easy to get confused trying to picture the set. Remember that the power set is a collection of subsets. There are some number of sets in this collection. We don't know how many, and what we want to figure out is if there is a function that can map the elements of A entirely onto the elements of the power set. Can we find a surjective map from A to P of A? Or will there always be an element of P of A left over? That's what we want to know. So we do this by making a particular subset of A. Remember, the set B is a set of elements from A. So B itself is a subset of A, right?
So that means that B is an element of the power set of A.
So what we need to find out is, were we clever enough in constructing B? Did we construct a subset that is not in the image of the function? Okay, that's what we're trying to do. So we're going to do that by assuming the opposite. That is, assume that B equals G of A0 for some A0 in A. Okay, so this proof is just really hard to get your head around. So we're trying to show that there's some element here that G does not map to, right? Okay, so we're going to assume the opposite, which means that there is one, that one of these elements does map to B, okay? So let's call that A0. So we're going to start here and then see if we can find a contradiction. Okay, so next we ask, does A0 belong to B or not? So let's assume that it is. Let's see what happens if A0 is in B. If A0 is in B, that is the same as saying that A0 is an element of A minus G of A0. That's just the definition of B. And since we defined B to be G of A0, this is the same as A0 is an element of A minus B. So if A0 is in B, then A0 is in A minus B, which means that A0 is not in B, right? Because if A0 is in A minus B, then it can't be in B. So that's a contradiction. Okay, so what if A0 is not in B? That implies that A0 is in A minus B, right? Because if it's not in B, then it has to be in A minus B. But then this means that A0 is in B because this is the same thing as A minus G of A0, and this is the definition of B. So if A0 is an element of A minus B, then A0 is in B. But we started by assuming that it's not. So again, a contradiction. So whether A0 is in B or A0 is not in B, either way we reached a contradiction. So that means that our assumption had to be wrong, and B does not equal G of A0. So that means that B is not in the image set of G, but B is in the power set. And that means that G cannot be surjective because we have an element in the range that is not in the image set. That's the definition of surjective, and therefore G is not surjective. Okay? Now, in order to prove, where did we start? What did we want to prove to begin with? Remember, what we're trying to actually prove here is that if A is a set, then there's no surjective map from A to the power set, and there's no injective map from the power set to A. We just showed that there's no surjective map. And remember, we started here by saying, just demonstrating that the existence of an injective map implies the existence of a surjective map. So if there is no surjective map, there cannot be an injective map. That's the contrapositive. And that's what we wanted to prove. There's no injective map from the power set to A, and there's no surjective map from A to the power set. So, as you can see, the proof actually isn't hard at all. But for me at least, getting my head around what we were doing here was very difficult. So, once you get it, the actual proof is quite straightforward. So, okay. So what we wanted to prove here, remember, is that the power set of the positive integers is not countable. And this proves that that's the case because there can also be no surjective map from the positive integers into the power set of positive integers. Okay, so this is another uncountable set. Okay, so this is the place to stop. We've now proved the existence of uncountable sets. We've seen two, but we've not yet mentioned the most familiar uncountable set of all, the real numbers, the set of real numbers. So you've probably seen that proof already, the diagonal proof, where if you list every decimal number, no matter how many of them you list, you can always read off one more by just going diagonal and making each digit different from one of the diagonal numbers. No matter how many you list, you can always come up with one more number. So if we assume that every real number can be represented uniquely with an infinite decimal, as long as they don't end with a string of nines, whatever. And we did prove this. When we were looking at the real numbers, we did prove that decimal expansions are a valid representation of real numbers. So we've proven that. Then we can prove the uncountability of the real numbers by using just a variation of what we proved here. It's just the diagonal proof with decimal instead of binary. But in some way, this proof isn't really very satisfying, right? And one reason is that the infinite decimal representation of a real number is not at all an elementary consequence of the axioms. And it actually takes work to even prove that the decimals are a representation of the real numbers. And another problem is that the uncountability of the real numbers does not, in fact, depend on the infinite decimal expansion of R, right? You don't need the infinite decimal expansion. They're not uncountable because of the decimal expansion. And in fact, the uncountability of R doesn't have anything to do with anything about the algebraic properties of R. It depends only on the ordering properties of R. But it turns out the uncountability of R is actually a topological result that requires a lot of topological machinery to get to beyond what we're planning on looking at for right now. So remember that what we're working on is only to prove rigorously L'Hopital's rule, right? That's what we're doing here. The proof of the uncountability of real numbers is related to compactness, however, which is the thing that we're heading toward that allows us to prove the extreme value theorem, which we need for L'Hopital. So when we get there, maybe we can go a little farther down this side road to prove that real numbers are uncountable in a more satisfying manner. We'll see. The thing is, After we learn about the fundamentals of topological spaces, I was planning on jumping back to Rudin because Rudin is much more rudimentary. I just invented a word that I'm very proud of. Rudin is much too rudimentary in his coverage of topology concepts. For now, though, this is the end of our study of set theory. The next time, we're moving on finally to topological spaces. We're going to define a topological space, and then we'll spend the next several videos going into some detail about them before moving on to the one that real analysis is based on, which is the metric space. Thank you.
Okay, here is the link to the first video in this chapter. Here is the link to the previous video. Here is the link to the next video. And click here to subscribe, and please join me on Patreon. The link to that is below in the description. Thank you.